Testing sound. Testing. Right. Okay. Good morning, all. We'll start. So, can you confirm whether my audio is clear and video quality is clear? Students? Morning, all. So, I check the audio from my end. It's fine, right? Okay. Okay. So, this is the first day we are meeting after the new year, right? So, wish you a happy new year before starting the class. This is the first year we are starting after the year, and this is kind of a milestone point, you can turn this around, right? That's important, right? Because now we are starting a new year with new hopes, new targets, new goals, right? Everything. So this is a good point that you can set your goal, right? This is a good point that you can set your goal, you can target high for this coming like 30 weeks of time, right? Now we are in the 30th week before the exam. So for this 30 weeks of time which is coming, this is a good point that you can set a high target, right? And work for that target. Work for that target during these 30 weeks of time, right? Now it's around 206, 7 dates are remaining, right? Something like that. Say 210, around 210 days are remaining, something like that, right? So set a target, set a goal, and work for that goal during these coming weeks, coming months, right? That's basically it. All right then. So we'll start. So as we planned in the revision today, we are going to start work, power, energy parts first, right? Work, power, and energy. One of the like critical parts, crucial parts when it comes to our questions, right? And Youths of the registered students are already posted. You will get it in the coming like 3 days, during coming 3 days. And if anyone registered new in this month, you will also get the tute within 3 days, right? So first we will be starting with energy parts here in the class. So before that, as usual, first we'll go to the rapid recall and recall what we have done in the last week before moving on to today's thing, right? So I think you can download the rapid recall paper under the respective week, right? So download rapid recall and start. Download rapid recall and start. You can get the rapid recall. Rapid recall 4 is uploaded, right? So we will start off with rapid recall 4. Right now the time is 8:34. 8:34. Right. So I'll give you 15 minutes until 8:49. Okay. Right. Rapid recall 4. So in the last week we have finished everything regarding Newton's laws, right? And this rapid recall is entirely from Newton's laws, what we covered in Newton's laws, right? Okay. Right. Right. All right. We'll start. Question 1. Right. Question 1. It says two objects A and B with masses 4m and m respectively are released from rest. Right. Determine acceleration, tension, evaluate normal reactions. Okay. Let's see. This diagram is given. Right. So this is rapid recall for question 1. Rapid recall for question 1. One object is here. It is attached to a pulley and another object is connected to here. This angle is given as 30. Right? The angle is given as 30. Right. And masses are 4m and m, A and B. Right? So this is 4m. Let me mark their weights at once. 4mg. Right? A. And this is B. Right? This is B, mg. Right. The first question is about accelerations. To find accelerations, right? To find accelerations, we have to know all the forces acting along the accelerating direction. Right? All the forces acting along the accelerating direction. Now it is going to be accelerated along the string now. Along the string. So you have to check the forces acting along the string. Then if you check forces here, right? If it is 30, 90, 90 minus 30 is 60, 60. This becomes 30 again. Right? Then this is 4mg cos 30 in this direction. And here 4mg sin 30 in this direction. Right? So we know 4mg sin 30 is 2mg. Sin 30 is half now. 4mg sin 30 is 2mg. And from this end, there are no any components from weight acts along the string. Right? That is perpendicular to string. Since there is perpendicular to string, there is no contribution from this weight here. So only tensions will be there. So let's mark tensions as T throughout. Let's mark tensions as T throughout. Like this. Okay. Now you can apply any equation. So there are two methods we discussed. In Newton's laws, there are basically two methods. One is you can consider these objects one by one separately and apply F equals ma and get 2o, 3o, whatever the required number of equations, and you can simplify them as simultaneous equations. That is one method, right? The other method is you can apply F equals ma considering the whole system at once along the string, right? So I will go with the shortest method. Then you can use F equals ma along the string. See, along the string direction now this is 2mg now. So this side is going to go downwards. So while that is coming downwards, this will travel leftwards like this. Right? Then we can say for system along the string. For system along the string, right? For your clarity, along the string direction now is this. Along the string direction now is this, right? Then along the string downwards you have 4mg sin 30. 4mg sin 30. All tensions cancel because we are considering the system. Tension is an internal force. So one component of tension cancelled off with the tension acts on the string at the same point in the opposite direction, right? So what we have marked here are tensions act on objects, right? So even though only 4 tensions are marked, there are infinite number of tensions acting on the string. And for all infinite number of tensions acting on the string, there are infinite number of equal and opposite tensions, which means they are mutual tensions acting on the string. And once you consider the system, tensions act on object get cancelled off by tensions act on the string. So therefore, all the tensions are cancelled off. All the tensions are cancelled off. All the tensions are cancelled off. Then nothing remains in this side. Mg is perpendicular now. So M is 4m plus m. 4m plus m a, right? So that's it. For mg sine 30 is half. This is 5m a, m2, m cancels, 2 to 4 cancels. Then a equals 2g over 5. Right? No need to simplify g because the question is given in labels. No need to simplify g because the question is given in labels. Unless you can simplify g as well. Right? If needed. Now in this particular requirement, there is no need. Right? Next. Raise your hand if you have got the same answer. Raise your hand if you have got the same answer. Asmita, good. Hamza, right, good. Okay, good. Second one, determine tension on the string. To find tension, this is number one, part one. To find tension, easiest way is we can apply F equals MA for B. Right? Only for B, leftwards, F equals MA. Right? So only F, only horizontal F belongs to B is T. Right? Mass of B is M. And acceleration of V is here, 2g over 5. Very straightforward. Tension equals 2mg over 5. Tension equals 2mg over 5. Tension equals 2mg over 5. Right? 2mg over 5. Third one. Evaluate normal reactions exerted on A and B by the flow. Normal reactions on A and B by the flow. Right? So I haven't marked reactions yet. This reaction on A will be perpendicular upwards like this. Let's say RA. This reaction on B will be perpendicular upwards like this. Let's say RB. Right? To determine RA and RB, you have to consider respective equilibriums. Consider respective equilibriums. Right? Somehow you have to check for an equilibrium. You have to check for an equilibrium. Right? Then for A, you can write by considering perpendicular equilibrium to inclined plane. Perpendicular equilibrium to inclined plane. Right? Perpendicular equilibrium to inclined plane. Perpendicular to inclined plane. Then that direction is, that particular direction is this. Right? That equals to its opposite direction. Then perpendicularly upwards we have RA, only RA. And perpendicularly downwards 4mg cos 30. Right? So we know cos 30 is root 3 over 2. Then 2 to 4 cancels, 2 remains. So RA becomes 2 root 3 mg. One reaction is here, 2 root 3 mg. 2 root 3 mg. One reaction is here, 2 root 3 mg. Right? And the second one, you can consider a vertical equilibrium of V. Right? Let me write here. By considering vertical equilibrium of B, vertically upward forces equals vertically downward forces. Vertically upwards we have RB vertical downwards, that is only mg. So rb equals mg. Right. Good. So raise your hand if you have got all answers correct. Raise your hand if you have got all these answers correct. Rasmita, okay. 1, 2. Right. So take down if anything. Take down quickly if anything. Take down quickly if anything. So are you doing physical classes? Yeah, if you need to know anything about the classes, let me pin my channel link and number here. Right. Let's move on. Second one. If all surfaces are smooth, determine the following: reaction exerted on B by A and reaction exerted on C by B. Right. Internal reactions. We discussed last day. Internal reactions. Right. right? So this is given ABC. There are three objects as ABC. Three objects as ABC, right? Right. And their respective masses are given capital M, then 2m and 4m, 2m and 4m. And the applied force on this one is F. They are ABC, right? A, B, and C. Right. Question one. Question one: reaction exerted on B by A. On B by A, on B by A is this. Say R1, then equal and opposite one of that is on A by B, R1. Right? They are equal and opposite. So first of all, we will need the acceleration, then apply F equals ma for system. For system, horizontally rightwards, F equals ma. Then only F remains in the system is this applied F. Total mass m plus 2m plus 4m, right? M plus 2m plus 4m into A. So simplify, acceleration is given by capital M plus 6m, right? F over capital M plus 6m. Now if you need R1, easiest way is you can consider this force frame. Easiest way is to consider this force frame, right? Then what you can do is for B and C, for B and C, rightwards, F equals ma. See how easily this is going to simplify. Only unbalanced force remains for this system B and C is R1. So R1 is coming at once, and mass of that particular system is 2m and 4m, 6m, into acceleration is here F over m plus 6m. So R1 equals 6mf over capital M plus 6 simple m. Okay, raise your hand if you have got this answer. Raise your hand if you have got this. Good. Others? Good. Okay, good, good. Very good. Very good. Next one. Reaction exerted on C by B. On C by B is this. On C by B is this. Say R2. An equal and opposite reaction of the same one will be on B as well as R2 like this. Right? So we need R2. Easiest way is consider only C. Then for C, horizontally rightwards, F equals ma. F is only F remains is R2, m is 4m, right? Acceleration is here, then 4m F4, m plus 6m. 4m F4, m plus 6m, right? Next. It is clear? Then question number 3. Question 3. It says two objects, A and B, are attached with a string of mass 2 kg. Two objects A and B are attached with a string of mass 2 kg. Respective masses of A and B are 2 kg and 4 kg. System accelerates upwards with 10 ms minus 2 when the shown force is applied. Okay, determine first one magnitude of F. Second one tension at the middle point of string. Right, heavy strings, or we discuss this as weighted strings. Heavy strings or weighted strings. Another good part we have here in Newton's laws. We had last day. Right. Let's see. The decrease incline A and B. applied force is F, right? A and B, 2 kg and 4 kg. So then this is 20 newtons, and here this is 40 newtons attached with a string of 2 kg. No? Then string itself also got 20 newtons. Right, and the acceleration is given 10 m minus 2. This is dragged upwards with this common acceleration 10 m minus 2. So now you know how accelerations are checked, whether they are common or different, that we discussed last day about different accelerations. So we know how the way that you check different accelerations using displacements. Now if you do the same here, you can clearly see that is a common acceleration, right? That is a common acceleration. So therefore nothing to think further. That is a common acceleration. No? That is a common acceleration. No? So it will be 10. Right. Then first one, magnitude of F. To find magnitude of F, since acceleration is known, now my thinking is to apply F equals ma. Masses are known and acceleration is also known, and we can write all other forces other than capital F as well. So which means we can isolate capital F somehow and find capital F. No? So that is how I think. Then mark other forces that is required. 20. So we know this angle here is going to be 30 degrees. No? This angle here, this is 30. Similarly, this angle here is also 30. And the angle here is also 30. Right? Then, if needed, at once you can write all the components as the addition. Right? If needed, you can write at once the all components as the addition. That is also fine. Right? So, or else, in the usual way, you can write the components one by one. That is also fine. Omari. See? For this one, the component here is 20 sine 30. And from this heavy string, again, a 20 sine 30 here. And from this one, this is 40 sine 30 here. Right? So I didn't write any cross components yet. That's it now. Then, considering system, so we know there will be tensions on the string as T1, T2 at the terminals, but when the system is considered, all tensions are cancelled off with their mutual tension acting on the string. Right? They will be cancelled off with the mutual tension. Then no worries. Apply F equals ma upwards the plane for system. Right? And upwards the plane we have this F here minus all tensions get cancelled. Here we have three forces, 20 sine 30, 20 sine 30 and 40 sine 30. So altogether that is 20, 20 is 40 and 80 no. So altogether if you write at once 80 sine 30. Addition. Right? 20 sine 30 plus 20 sine 30 plus 40 sine 30. Right? I wrote the addition at once. MA, right? Total mass 2 plus 2 plus 4. 8. Right? So F minus, we know sine 30 is half, then 80 sine 30 is 40 equals, this is 8 no? 8 and acceleration is also given. So let me plug it here. Acceleration was 10. Then 8 times 10. 8 times 10. Right? That is 80. Then F equals 80 plus 40, 120 newtons. 120 newtons. Right? A little bit different idea from what you are getting in traditional questions, usual questions. Right? Raise your hand if you have got 120. Raise your hand if you have got 120. Okay, there are good. Good. Take it down if anything. Take it down if anything to be corrected. Good. Right. Then tension at the middle point of string. So we know if we need to determine, right, this part one, this was part one, and part two, tension at the middle point of the string, right? So we know, listen, we know if we need to determine tension at any middle point of a system, right? Tension at any middle point of a system, you have to break the system from that particular point. You have to break the system. Have to break the system from that particular point, right? Then I'm going to break the system at this middle point, and always tension forces remain as attractions at the point of intersection, at the point of breaking. Tension forces remain as attractions at the point of breaking, at the point of intersection, right? Then you can consider any side. I'll be taking this side, this force frame for my calculation, this one. Then for your clarity, this is the force frame. I'm going to consider half of the string. Half of the string means 1 kilogram here, and A is there, A is 20, right? A is 20 means this component of AX, that is 20 sine 30, right? And here the tension remains as an attraction, say T, and component of weight of the string, right? Component of weight of the string also acts along the string like this. Only half of the string is here, then 10 sine 30, right? 10 sine 30. That's it. Apply F equals ma upwards. F is T minus altogether 20 sine 30 and 10 sine 30 means 30 sine 30 equals total mass 2 plus 1, right? A is 2, no? Total A is included 2 plus 1 into A, acceleration 10, right? That's a common acceleration. That was a common acceleration. Then T minus 30 sine 30 is 15. 3 times 10 is 30. T equals 45 newtons. Okay, raise your hand if you have got 45 newtons. 45 newtons. No one? Is that so? Is that so? On. Okay, take it down. So likewise, you should be able to tackle it adapting to given scenario, right? When I discussed the questions last week, I think I didn't discuss any heavy strings on inclined planes. Now what is given here is a heavy string on an inclined plane. For that, you have to adjust with the learnings you got so far. Right? How to adjust with the learnings we got so far. You have got so far. Okay, finished. Let's move on. Right. Theoretical is done. Let's move on. Okay, listen. Right, listen. Okay, so let's move on. So as we planned, today we'll be starting off with energy and the parts rolling out in the coming weeks are today we'll be looking at the full aspect of energy, work, power, right? We call work, power, and energy, work, power, and energy. And in next week, we'll be doing linear momentum, right? Linear momentum, impulse, collisions, everything. And the next week, we'll be starting equilibrium of forces, another very important and very much critical and crucial lessons in our lineup, right? And then after equilibrium, we are planning to move towards center of gravity. So that's a plan during the month. That's a plan during the month. Yes, so we'll start. Write down next heading energy. Write down the heading as energy. Energy. Okay. So first I'll start off with a question. Any idea about what energy is? What you know so far? Any idea about what energy is? What is energy? Anyone? Any thoughts? What energy is? Any thoughts? Even if you are on YouTube, you can put it to the live. Right? Even if you are on YouTube, you can put it to the live. I mean live chat. Any idea? Any idea? I didn't ask for definitions. Just tell me your thoughts about what energy is. Right? Just what you know. Capacity or ability to do work. Correct? Good. Good. Yeah, that is actually correct. That is correct. Good. So simply, listen, simply, energy is ability to do work. Energy is ability to do work. Right? So we'll see what work is. Right? Next, energy means if a work is done, that ability is called energy. That ability is ability to do work. Ability to do work is called energy. Okay, write down first. Write down first. First point, the ability, the ability, the ability, the ability, the ability to do work. The ability to do work. The ability to do work is called energy. Is called energy. The ability to do work is called energy. Right. Next question. Next question. Is it a scalar or a vector? What about energy? Scalar quantity or a vector quantity? Quickly. Is it a scalar or a vector energy? From units and dimensions, we are getting very small idea, that idea, right? Energy is a scalar quantity. For energies, they don't have any direction when we say energy. Now, as an example, say it's about a kinetic energy. It's about a kinetic energy, irrespective of the moving direction of the object, right? If there's a velocity, there's a kinetic energy, right? And again, as an example, let's say we talk about heat energy. Heat energy, right? Heat energy is all about heating an object or cooling an object, right? So when this is heated by let's say 10 degrees Celsius, can we say the direction of this heat energy is this? No, there's no energy. There's no energy, right? Heating objects, cooling objects. So we started in 26th theory class, thermal, right? Heating, cooling, expansions, right? Expansions of liquids. All right, next point. Next point, use a red pen. Energy is a scalar quantity. Use a red pen. Energy is a scalar quantity. Energy is a scalar quantity. Energy is a scalar quantity. Right. Then as a subheading, write down forms of energies. Forms of energy. Forms of energy. Forms of energy. Yeah. Quickly tell me, what are the forms of energy you already know? What are the forms of energy you know? Forms, so we can say types. Types of energies. Tell me, what are the types of energies you know? Quickly. Quickly. What are the types of energies you know? Put it to the chat. Kinetic, correct. Kinetic energy. What else? What else? Yeah. When you say potential, we have to say which potential, because there are different types of potential energies, right? So one is gravitational potential energy. Gravitational potential energy, right? And we have elastic potential energy. This is also called strain energy. This is also called strain energy, right? Also called strain energy. And what else? Heat, sound, thermal, good. Heat energy, or we can say thermal energy. Heat energy. Sound energy, correct. What else? Right? Another very popular one that we will be discussing. Another popular one that we will be discussing in radiation. Nuclear energy. Nuclear energy. And chemical energy is also correct. Chemical energy, nuclear energy. Right? So there are more forms. There are more forms. Nuclear energy, etc. Right. Take it down. Take it down. There are more. There are more. So here I mentioned main types of energies that we will be seeing in our syllabus. But you will be seeing in the syllabus, in our syllabus. And the other announcement is that I forgot to give you at the beginning. The other announcement is we are starting the reverse class this Saturday, right? The coming Saturday is 6th. Sorry, 10th. 6th again, another 10th. 10th of January. So we'll be starting it on 10th of January from 7 p.m. to 10 p.m. the reverse class. So in the reverse class, I'll be starting unit 10 properties of matter, right? We'll be starting off with unit 10 properties of matter. So if you are registered for the revision class, right? If you are registered for the revision class, it'll be free, right? It'll be free. You can attend the reverse class free. And if there's anyone who needs to join only for the reverse class, right? Not attending to the regular classes. So what you can do is you can also join, right? Doesn't matter whether it's 26 or 27 for both students, that's open, because we are starting something from the back end of the lessons, right? Which they don't have much connections with the previous parts, right? Much links with the previous parts. And so if there are any friends or colleagues that they need to join the class, you also can share the message, you can pass the message. And yes, so then you will be doing the regular revision class here on Tuesdays. We will be having the regular revision class on Tuesdays here from 8:30 to 2, and the reverse class on Saturdays, right? You have to join both, because the lessons that I am going to cover in the reverse class will not be covered again in the theory class, because no need to do a duplication, no, right? You can cover it up from the reverse class, and the purpose to start the reverse class is to cover them faster, right? That's a whole purpose. So therefore, join both classes and you can cover all the things, right? Finish? Okay, finish now. Right. Then let's see these two types first, because the reason is, so under mechanics we'll be focusing on mechanical energies, right? These two are called mechanical energies. If you don't know, you can put a curl bracket for these two, kinetic energy and gravitational potential energy, and label it as mechanical energy. A single term for kinetic energy and gravitational potential is mechanical. They are called mechanical energies. They are called mechanical energies. Mechanical energy. Right. Now, under mechanics, listen, under mechanics, we have only mechanical energies. Right. Under mechanics, we have only mechanical energies. But all other energy forms, types are also there in our syllabus now. As an example, you will see elastic potential energies and strain energies in oscillations and elasticity, and heat energy in thermal, sound energy in waves, right? That in waves, nuclear energy in matter and radiation. So likewise, it will roll out in the coming parts, coming units. Okay then. So let's start with kinetic energy. Subheading 1, kinetic energy, right? Subheading 1, kinetic energy. Kinetic energy, right? Within brackets Ke, right? So first, as an equation, we can say kinetic energy is half mv squared. Kinetic energy is half mv squared, right? Take down the equation and highlight. Then we'll introduce terms m and v. Take down. Write down. Introduce terms. Introduce terms. M, mass. Symbol M, mass. symbol M, mass. V, speed dot velocity. V, speed dot velocity. Right, speed slash velocity. Right, speed slash velocity. Speed dot velocity. Right. Right. A small task. Listen. A small task. Quickly find units and dimensions of kinetic energy. Find units and dimensions. Find units and dimensions of kinetic energy. Find units and dimensions of kinetic energy. Find it quickly and send your answers. Right, quickly. Yeah. So when you find units, right? When you find units, there can be derived units as well, right? But ultimately, what we are going to focus is only the SI, right? See, half M is called no. There are no units for coefficients. Half is a coefficient. Then units of kinetic energy is given by units of M into units of V squared. Units of M is kg, right? Units of velocity or speed is ms minus 1 whole thing squared. So this is kg m squared s minus 2. Kg m squared s minus 2. Right? So this is one derived unit you can have. Right? One derived unit we can have. We know newtons can be written as, see how I'm going to use this idea. So we know units of newtons is kg ms minus 2, no? Right? That you can take from F equals ma. Units of newtons is kg ms minus 2, which means that is inside this answer. We can rewrite this, right? We can rewrite this as kg ms minus 2 times m. No change, right? No change for the answer. So you can rewrite this as this. Give me 1 second. So no change in the answer. So you can rewrite it this way. Then here, this is newtons. So the second derived unit is Newton meters. Second derived unit is Newton meters. Right? But the SI is, right? But the SI is joules, that is correct. Joules, third unit, and this is the SI. Right? So you better mention all. I mean, for the proceedings, we'll be stick to joules. But you should know what the derived units of energy as well, right? There are two derived units like this. Newton meters is very popular when it comes to energy, right? Newton meters and kgm squared is -2. Okay, if you need dimensions, right? I will do the dimensions here. If you need dimensions, we know coefficients are dimensionless. Then dimensions of m into dimensions of v squared, right? Capital M, v is Lt minus 1, it's a velocity squared. Then simplify ml squared t minus 2. So dimension is ml squared t minus 2. Right? These are the units and dimensions of kinetic energy. Write down. Units and dimensions of kinetic energy. Take down. Right? Let's move on. Then number 2, gravitational potential energy. Right? From number 2, gravitational. From number 2, gravitational potential energy. Number 2, gravitational potential energy. Right? GPE, gravitational potential energy. Right? So as an equation, gravitational potential energy is mgh. Take down and highlight the equation mgh. Right? Right? Introduce terms. M mass, G gravitational acceleration, M mass, G gravitational acceleration, H. H is the most important term here in mgh, right? H is the most important term here in mgh, right? What is H? H is the vertical height. Listen, don't write. Listen first. H is the vertical height from Earth zero level to center of gravity of object, right? Earth zero level to center of gravity of object, right? So we'll see what an Earth zero level is in the next part, right? So two important things. These are vertical height, right? Vertical height from Earth zero level, not the ground, right? You can't say it's ground. From Earth zero level to center of gravity of object, right? Not to the topmost point of the object, to the center of gravity of object. When we are dealing with particles, the particle and center of gravity will be the same point. But when we have other types of objects, right? Non-particle objects, right? It should be measured up to center of gravity. Okay, introduce H and better to use red for H. Better to use red for H, right? Introduce H. Vertical height from Earth zero level to Earth zero level. Vertical height from Earth zero level to vertical height from Earth zero level to vertical height from Earth zero level to center of gravity. Earth zero level to center of gravity. Vertical height from Earth zero level to center of gravity of object. Vertical height from Earth zero level to center of gravity of object. So write down below with a red pen, put an asterisk mark, and write down. Earth zero level is, write down. Earth zero level is Earth zero level is any hypothetical Earth zero level is any hypothetical arbitrary Earth zero level is any hypothetical arbitrary level we can consider when solving sums. Okay, then write down sign convention, right? Next, subheading sign convention when writing H, when writing simple H. Sign convention when writing simple H. Sign convention when writing simple H. Right. See. Now, assume this as the Earth zero level. We denote Earth zero level as this equals 0. Earth zero level equals 0. Right. All the distances measured above the Earth zero level. All the distances measured above the Earth zero level are considered as plus, and all the distances measured below the Earth zero level are considered as minus. Right. So there's a reason behind energies, work and energy, to measure this in this way, right? I'll explain the reason in the coming parts with the work, right? Then you will understand this better, right? Otherwise, this is not something meaningless, right? The meaning is coming with a respective meaning we have in work, right? That is how this plus and minus comes. Since we need to mention it here under gravitational potential energy, we are mentioning, just know that all the distances measured above the Earth zero level are plus and below the Earth zero level are minus. Mention this. Right? Write down below with a red pen. Write down below with a red pen. Put an asterisk mark and write down distances measured. Write down in red. Distances measured. Distances measured. Distances measured above Earth zero level. Distances measured above Earth zero level. Distances measured above Earth zero level. Distances measured above Earth zero level are considered as plus. Are considered as plus. Are considered as plus. And are considered as plus, and distances measured and distances measured below Earth zero level and distances measured below Earth zero level are considered as minus. Right. Then as the next point write down, keep using the red pen. As the next point write down, stored energy. Sorry, before that. Sorry, don't write. Let's introduce work first. Right? I didn't introduce work yet now. Next heading, work. Next heading, work. Next heading, work. 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 So what is work? Any idea about what work is? Now, before we checked about energy, now we are in work, right? So I didn't check the units and dimensions of gravitational potential energy again, because that is also same, no? That will be same. That is also same, right? That's why we didn't check. In work, we will check again and we will come to a conclusion. What is work? Any idea? Anyone? Again, don't need definitions. Tell me if any idea you have, right? Don't Google or ChatGPT and tell me, right? Just your thoughts in your words. What is work? What is work? According to what you know. Quickly. Anything? What is work according to what you know? No idea. Right. Work is something like this. Work is the transfer of energy. Work is the transfer of energy when an object moves from or displaces from one point to another. Right? When an object displaces from one point to another, there is a transfer of energy. That is called work. Write down below. Write down below. Transfer of energy. Transfer of energy. Transfer. Transfer of energy. When an object displaces, transfer of an energy. Transfer of energy. Transfer of energy. When an object displaces. Transfer of energy. When an object displaces from. When an object displaces from one point to another. When an object displaces from one point to another. Is called work. Is called work. Right. See? So this is the equation of work. This is the equation of work. Work can be written as F into S, or we can say F into D. Both are fine. Right? Where F is, right? Whereas F is force and S is very important. S is parallel displacement to force, right? S is only the parallel displacement to this applied force. The parallel displacement, not the perpendicular displacement, right? It's a parallel displacement. Okay, take down the equation and we'll introduce terms. Take down the equation. And introduce terms. F applied force or force. F force, F is force. S is the most important one here. S is the most important one here, right? S, write down. Parallel displacement, parallel displacement to force, parallel displacement to force, parallel displacement to force. Right. Now, as an example, it is like this. As an example, it is like this. See, look at the board. Say initially, an object was here, right? Initially, an object was here. Let's say this is where the front end of the object is. Look at the board. At t equals 0 initially, and a force F is applied on the object like this. A force F is applied on the object, and as a result of this, this object displaces from here to here. The object displaces from here to here. Right now, this front end of the object is here. At t equals t, let's say a time t has spent, and if the displacement from here to here is d, right? Work done can be written as, so W can be written as, work done can be written as force times parallel displacement, no? Then the work done here is Fd, right? Take this down as an example, example 1. This is example 1. Take down example 1, right? And this one example 2. Take this down, example 1. And here, this is example 2. Two forces are acting on this, F1 and F2. And try to write work done in this scenario. Try to write work done in this scenario, total work done in the scenario. Try to write total work done in the scenario. Let's see. Okay, let's see. Here, total work done is, see, here, total work done is for F1, right? For F1, there's a parallel displacement L, F1 into L. Plus for F2, there's no parallel displacement into 0. Right? Important, very important. There's no parallel displacement for F2. So therefore, total work done in the scenario is F1L. Total work done in the scenario is F1L. Third one. Third one. Try to write work done in question 3. Example 3, not the question 3. Example 3. Say this is D again. Try to write work done in example 3. Right? What about this one? What about this one? Any answers? Work done here in example 3. What about the work done here? Work done here in example 3. Anyone? Anyone? Quickly. Work done here. No answers? See? So first, since I don't have a direct displacement in this given direction of the force, since I don't have a direct displacement in the given direction of the force, right? We can dissolve this and approach the question. So away from the angle, right? We have f sine theta downwards. This is towards the angle. We have f cos theta, right? F cos theta and f sine theta, like this. Now do the same like this. Then total work done is work done due to f cos theta, right? There's a parallel displacement for f cos theta as d plus then work done due to f sine theta. There's no parallel displacement for f sine theta. It only moves along this plane, which means 0, right? So W equals f cos theta d. W equals f cos theta d. Got it? Raise your hand if that is clear. Raise your hand if that is clear. The way you write work. Clear? Right. Okay. Write down. Right. Okay. Another question. Listen. So work is force times displacement. No, force into displacement. Force is tell me, force. Is it a vector or a scalar? Force. Is it a vector or a scalar? Force. Is it a vector or a scalar? Force. Very straightforward. Force is a vector. Right? Straightforward. Force is a vector. What about displacement? Vector or a scalar? That is also a vector. Right. So work is a product of two vectors. Then tell me whether work is a vector or a scalar. What about work? It's a product of two vectors. Is it a vector or a scalar? Work quickly. Listen. Now, even though work is a product of vector two vectors. Okay, work is a product of two vectors. Ultimately, work is a scalar, right? So you can't say that when two vectors are multiplied, again a vector comes. You can't say, right? So if you are doing combined maths, you know it in the cross product and dot product of vectors, right? Because the product of two vectors can be a scalar as well. That you know if you are doing maths, if you are doing combined maths. So if not, just know that so you can't say whether the product of two vectors is a vector or a scalar. It can be both. It can be both, right? So this is a special case. Even though it is a product of two vectors, work is a scalar, right? If there's only one vector, right, in the product, for sure we can say that's a vector. Now, as an example, linear momentum. As an example, linear momentum, P equals mv. Mass is a scalar, velocity is a vector. The product of scalar and vector is always a vector. The product of scalar and vector is always a vector, right? That you can say, but scalars can be derived by the product of two scalars or two vectors as well. This is such a case. So work is also a scalar. Next point, keep using red. Use a red pen. Use a red pen. Work is also a scalar quantity. 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 Right. Again, a small task. Find units and dimensions of work. Quickly. Find units and dimensions of work. Find units and dimensions of work. Right. I need these two. Units and dimensions. Quickly. Right. Let's see. Right, let's see. Work is units of F into units of S. Right? So F can be measured. It's a force, newtons, and displacement is in meters, Newton meters. So this is one of the units, right? So if I do the same as before, the same thing what I did in kinetic energies, right? Same thing. Newtons can be expanded as newtons. kgm is minus 2, no? So same thing. kg m squared is minus 2, right? This is actually called the fundamental units. Fundamental units, right? This is derived, and the SI is joules. Newton meters, no? Newton meters are defined as joules. So this is the SI. This is SI. Joules is SI. Right? And dimensions of force into dimensions of displacement. Dimensions of force into dimensions of displacement. Dimensions of force mlt minus 2 into displacement L. So that is ml squared t minus 2. ml squared t minus 2. Right? Now, from the previous answers, I mean previous units and dimensions we obtained for kinetic energy, right? So it basically covers energy, and the work you can see all units and dimensions of work and energy are same, right? So the idea here is right, units of energy and work are also same, right? And dimensions of work and energy are also same, right? Write down below with a red pen. Write down below with a red pen. Write down below units and dimensions of units and dimensions of units and dimensions of units and dimensions of energy and work are same. Units and dimensions of energy and work are same. Units and dimensions of energy and work are same. Right. Listen. So as an next heading, write down as an next heading, write down relationship between work and energy. Next heading, relationship between work and energy. Relationship between work and energy. Okay, look at the board. Right, look at here. Relationship between work and energy. Right. See, so let's take a scenario where this object is taken to this point here, that is, say, h distance above. Right, this is an object of mass m. Let's say this is an object of mass m. Right, look at the board. Look at the board. And if this mass is m, we know weight of the object is mg, and applied force on the object is, let's say, Applied force on the object is F. Applied force on the object is F. If I need to take this upwards, if I need to take this mass from here to here, let's say points A and B, then that'll be easy for our discussion. No? So this is point A, this is point B, right? If this object is taken from A to B, tell me what is the minimum force required, minimum F, what is the minimum F required to take this from A to B? What is the minimum F required? Minimum. Quickly. What is the minimum F required to take this from A to B? Minimum value of F. Any idea? What is the minimum value of F required to take this from here to A to B? Minimum value. Minimum value. Minimum value is also mg, because if we need to lift it up from the surface and if you need to take it from here to here, right? So we have to apply another counter force for this mg, no? When F is exactly equal to mg, right? We know that is an equilibrium. That is an equilibrium. But that is considered as a minimum value. If that applied force is even a bit, right? A tiny bit is greater than mg, it goes up, no? Even a tiny bit is greater than mg. So therefore, minimum value is F. Minimum value of F is mg. Right. Now, what I'm trying to do is, right? What I'm trying to do is, I'm going to write work done from A to B. We know work equation, no? We are going to write work done from A to B. See? Work done from A to B. Right. Then our equation is W equals F into S. Right? Fs. Then work done is, so we know minimum F equals, right? F min. Minimum F equals mg. Minimum F equals mg. Right? Then F min is mg. New displacement from A to B is h. Right? Then the work done here is mgh. Work done here is mgh. Right? Work done here is mgh. Right. Now, keep it aside. Keep it aside. So we know when an object is taken from one point to another, its potential energy changes. Right? Its potential energy changes. Gravitational potential energy changes. And compared to this point, potential energy at a higher point is higher because mgh, right? When you go upwards from the earth zero level, it gets higher. Now to write potential energies, let me consider earth zero level here. Let me consider earth zero level here. Say, let me consider the earth zero level here. Right. Right. Now, separately, if we write stored energy at B, stored energy at B. Look at the board. Stored energy at B, right? So we know there's no energy stored at A because that is at earth zero level, right? There's no energy stored at A because that is at earth zero level, right? So we can write this as delta E from A to B, and it is total energy at final point minus total energy at initial point. Total energy at final point is, there's no velocity. If there's no velocity, there's no kinetic energy. But this is h distance above earth zero level, right? H distance above earth zero level, then mgh, right? No kinetic energy, 0. Minus at A, object is at earth zero level, then mgh is also 0 because h is measured from earth zero level. No? if there's no velocity, no kinetic energy. Then stored energy here is also mgh. Stored energy here is also mgh. What is the idea we can take from this? Listen, right? An important idea for the proceedings. The idea you can take from this is, listen, the idea you can take from this is stored energy on the same object is equal to sorry, stored energy of the same object, energy 0, is equal to work done on the same object, which means simply work done equals stored energy, or work done equals transfer of energy. That is how we define work. Can you remember? Because work was the transfer of energy, which means that amount of transfer of energy should be equal to work now. So that is what we just proved. Take it down. Then I'll give you the note. Take it down. Take it down. Right. Right. So the final takeout from here is, right? Final takeout from here is work done on object equals, right? Equals what? Transfer of energy, right? Work done on object equals transfer of energy, right? Take this down and highlight. Take this down and highlight. Okay, write down below with a red pen. Write down below with a red pen. Okay, so before writing, first listen again. Listen again. Now, when work is done, listen. This is a important idea, very important idea we have here in work and energy. When work is done, right? In order to identify which party has done the work, right? By whom the work is done, there's a sign convention here, right? To identify by which party, by whom the work is done, there's a sign convention. Sign convention, right? So we have another sign convention in optics, no? So likewise here also these are sign convention, right? That sign convention is like this: work done by externals. Externals means us, right? Externals means us. Work done by externals are defined as positive work, right? As an example, let's say the pen is initially here. This pen is initially here, and we need to take this pen, right? We need to take this pen from here to this point. You need to take this pen from here to this point, right? That doesn't go automatically, right? It don't go upwards naturally. So we have to apply a force here and do it by ourselves, no? That is called an external work, right? So in such a case, now if I relate it to this scenario, now in this scenario, this work done by us is mgh, right? Plus mgh, and if we need to take this pen again from here to here back to the initial point from here, see, it comes automatically, it comes down automatically, it falls down, it comes down automatically. Then in that case, we didn't do any work, I didn't apply any force, I just release this, so it comes down automatically. So in that case, work is done by the field in the sense, right? Field in the sense, the gravitational field, or we can say work is done by the earth, right? Earth කියලා කියන්නේ, that is exactly the gravitational field of earth, right? So based on that, there's a sign convention of positivity and negativity for work done, for the ease of identifying which party has done the work, right? Who has done the work, right? It's clear now? Mention below with a red pen. Mention below with a red pen. In work slash energy applications. 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 Work done by externals. Work done by externals. Work done by externals. Work done by externals. Within brackets, us. Within brackets, us. Within brackets, us. Is considered as positive, is considered as positive, within brackets plus work, is considered as positive within brackets plus work, and work done by gravitational field, and work done by gravitational field, and work done by gravitational field. Work done by gravitational field. Within brackets, Earth. Within brackets, Earth. Work done by gravitational field. Within brackets, Earth. Is considered as negative. Is considered as negative. Is considered as negative. Within brackets, minus work. Okay, right? So take this down again below. Earth zero level, and the object is taken from here to here. Let's say A to B, right? Sorry. And say this height is h and this is m, right? First point, when object is taken from A to B, when object is taken from A to B, right? Work done from A to B, WAB, is plus mgh, right? And this is when object is falling from, when object is falling from B to A, right? WBA, that is minus mgh, right? Take it down. Okay, raise your hand if everything is clear up to this point. Raise your hand if it is clear up to this point, right? And if any questions you can ask so far up to this point quickly. Right. Okay. Afil, what happened? Fell asleep? Huh? Fell asleep? And got up only by now? Is it? Right, let's move on. Let's move on. Next heading, power. Next heading, power. Power. Okay, again, what is the idea you have about power? Any thoughts? Any thoughts? What's the idea you got about power? What's the idea you have about power? What is power? Anyone? Now, if you are on YouTube, you can respond your answers. You can put your responses to the live chat. What is power? Any idea? Work done by time. Work done by time. Any other answers? Anything else? Right. Listen. Power is defined as, listen, power is defined as the rate of work done, the rate of doing work, the rate of doing work or rate of transfer of energy, right? Rate of transfer of energy or the rate of doing work is defined as power. Okay, write down first. Write down first. The rate of work done. Write down. The rate of work done. 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 Or the rate of energy transfer. The rate of work done or the rate of energy transfer. Rate of work done or the rate of energy transfer is defined as power. Is defined as power. Right? So therefore, you can write power either as work over time or energy over time. Right? Either as work over time or energy over time. You know, anything over time is defined as a rate, no? Anything divided by time. Anything divided by time is defined as a rate. Right? Now, delta S over T, right? Velocity, you know velocity is delta S over T. Then rate of change of displacement, rate. Over time is a rate. And acceleration, rate of change of velocity is acceleration. So likewise, anything over time is a rate. So this is rate of work done or rate of transfer of energy is defined as power. Right. Next question. Next question. First tell me whether power is a scalar or a vector. What about power? Is it a scalar or a vector? Work over time or energy over time? Scalar quantity or a vector quantity? That is obvious. That is a scalar quantity because this is a scalar divided by a scalar. Work is a scalar we know from the previous step, and time is a scalar that you know from common sense. Right? A scalar by scalar is a scalar. Write down below with a red pen. Power is also a scalar quantity. 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 Right. Again, a small task. Listen. Again, a small task. Find all units and all units, find all units and dimensions of power. I need you to find all units of power. All units, all units of power and dimensions of power. Start now. All units of power and dimensions of power. Start now. Send me your answers. Okay, good. Let's see. Good. So first, I'll start with this one, work over time and units of work. So first we can plug units of work as, right? Units of work as joules. No? Work is in joules. Time is measured in seconds. Right? Then from here, J is minus 1. This is 1 unit. J is minus 1. Right? 1 unit. And then we can expand joules as Newton meters. You can expand joules as Newton meters. Right? When you do the expansion, listen, a small trick, right? A small trick, listen. When you expand joules, right, you can either use the unit itself and expand, or you can come to the equation here and do the expansion. Totally fine, right? If you expand work as F into D, right, again it does the thing, right? Or else you can just check the unit and expand as well, right? Either way is fine. Now joules, we know that is Newton meters. Then joules is Newton meters over seconds, no? Which means that is NMS minus 1. NMS minus 1, this is also a possible unit, unit 2. There is also a possible unit 2. Not NS minus 1, NMS minus 1. Rasmita. Right? Then again check, is there any expandable units? Yes, there are newtons. So we know we can expand newtons as, let me expand here, newtons as kg ms minus 2 newtons into meters over seconds. What is happening now? Now it becomes kg m squared s minus 3. Kg m squared s minus 3. This is another unit. This is actually the fundamental unit, right? The way, listen, the way that you need to make sure that it is the fundamental unit is check whether all the units included in the answer, all the units included in the final answer are fundamental units. See, kilograms is a fundamental, meters is a fundamental unit, seconds is a fundamental unit, which means this answer cannot be expanded further. This cannot be expanded further. So 3 units up to here, and the SI of this is, right? SI of this is watts, right? Watts. This is the SI. This is the SI. So altogether 4 units. Altogether 4 units. 4 units altogether. Right. Dimensions. That is easy. Dimensions. Dimensions of work over dimensions of time. Dimensions of work is ml squared t minus 2. We proved before over t. So this is ml squared t minus 3. ml squared t minus 3. Right? Okay. So these are the answers. We will stick to what's here onwards. But you have an idea about, you should have an idea about the other derived quantities, derived units as well. Okay. Make changes if anything. Make your changes if anything. Right. Next. Listen. Next. The next idea is, see, See, furthermore, so we know P equals work over time, no? But we know how to expand work. How to expand work? Work is force times displacement, Fs. Right? Then plug that here. Then work can be written as F into S over T. The same thing can be written as F times S over T. No? This is a known value, S over T. Displacement over time. Displacement over time. Again, we know velocity equals displacement over time. Delta S over delta T, or displacement over time. Which means S over T is a velocity. Displacement over time is a velocity. Then P equals Fv, P equals Fv, another equation, another form actually, another form of the equation of power. This is a general equation of power. So using the general equation, if we need to connect it with a velocity, right? This is another equation we can use, right? So starting here, right up to this point. Right, introduce terms F force, introduce terms F force, V speed or velocity, speed or velocity, speed or velocity. Right. Now we have identified, you have seen all the equations of work power energy parts, and we have identified the background, and I didn't do any applications yet, right? So far this is all about the theory part we have here. This is all about the theory part. So starting from like 9, now we have spent around like 2 hours of time for these theory parts, right? So after the rapid recall, I think we started the lesson around 9 or 9:10 or something like that. And from that point up until here, it was all about theory parts. One second. It was all about theory parts. Okay. It is all about the theory parts. So first tell me, I mean, before moving on to applications, first tell me, any questions up to here? Raise your hand if everything is clear, and you can ask if there are any questions quickly. Okay, good. Okay, let's move on. Let's move on. As an example, take this down. Example. Example 1. Write down. Write down. A particle is. Write down. A particle is. A particle is. A particle is released from rest. A particle is released from rest at a point. A particle is released from rest at a point. A particle is released from rest at a point. A particle is released from rest at a point. Determine, 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 determine the velocity, the velocity, determine the velocity of particle after, determine the velocity of particle after falling a vertical height simple h. After falling a vertical height simple h. After falling a vertical height simple h. Okay, listen. Listen. So before thinking about energies, listen. Before thinking about energies, this is a known motion. First tell me, which type of a motion is this? Which kind of a motion? Which type of a motion is this? Which type of a motion is this? Quickly. This is a motion type you already know. Which type of a motion is this? Quickly. What's the type of the motion? What are the motion types we have? Linear motions, projectile motions, simple harmonic motions, right? Then rotational motions, circular motions, helical motions. So which type is this? Linear. This is linear, right? Since it is a linear motion, you already know how to solve this. You already know how to find this V, right? So first, before doing anything using energy, right? Before doing anything using energy, to you to see the difference, to you to understand the difference and the compare and contrast these two for the comparison purpose, right? First, I want you to try this using linear motion, right? You know linear motion already, and it was the first lesson we started in this revision class, right? Very first day, on the very first day, a month back, right? Okay, then this is what I need first. As method 1, you can take down the diagram. As method 1, write down using linear motion equations. Okay, try this. Try this using linear motion equations and tell me what this V is. I asked about velocity after falling a height h. No? Right. We need the velocity after falling a height h. Then let's consider velocity of the object here as V. We need V. Find this out and tell me what is it. Use a linear motion. Use a linear motion equation. right? Any answers quickly? So what is V? If you use linear motion equations, right? Quickly. Anyone? So that's an easy one. So what is the answer if you use linear motion? What is it if you use linear motion? See, time is enough. See, say this point is A and this is B. If I use a linear motion from A to B, right, downwards, use an equation like V squared equals U squared plus 2S, right? Very straightforward. Then V squared is V squared, U is 0, 0 squared. Then 2, acceleration due to gravity is acting downwards, G, fallen height H, right? Then it says V squared equals 2GH. So V equals root 2GH, right? V equals root 2GH, root 2GH, right? This is what happens if you use linear motion. This is what happens if you use linear motion. And this we already know. This we already know. Now, today we are going to look at the energy aspect of the same thing, right? Energy aspect. What is happening when using energies, right? So before using energy, listen, before using energy, there's one more thing to know, right? So we'll take this down as a note. Take down. So first do this calculation, and as a note, take this down. As a note, take down law of conservation of energy. Write down law of conservation of energy. Write down note law of conservation of energy. Law of conservation of energy. Okay, write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Total energy of N. Total energy of N. Isolated system. Total energy of an isolated system. Total energy of an isolated system slash a closed system. Total energy of an isolated system slash a closed system. Total energy of an isolated system slash a closed system is conserved. Total energy of an isolated system, a closed system slash a closed system is conserved. Right, listen. A closed system or an isolated system means a given system that we can consider as a system, as a closed system for a given instance, right? Now, as an example, listen. Now, starting from here, right, I can consider myself as a closed system. And again, if we go further, we can consider this closed room as a closed system. And if we go further, right, we can consider this building as a closed system. And again, if we go further, we can consider this whole earth is also as a closed system. And if we go further and further, we can consider this whole Milky Way as a closed system. So likewise, starting from very macro level, from micro level up to macro level, right? Starting from a micro level to macro level, right? All the systems that we are considering for a question are closed systems, right? They are called closed systems or isolated systems, right? Closed or isolated. That's the idea. Now, in this scenario, there are only two objects we are considering, no? Then for this question, these two objects, this one object with 2 points, not two objects, one object with 2 points is a closed system, right? Is a closed system, something like that. Which means now, at the moment that you are doing this question, we assume that we have only this object in this story. We have only this object in this space. That's it. That's the idea. There's no any other objects. There are no any other obstacles. Only this one is there for this whole space. That's the idea. That is called a closed system, right? Then what it says is, if total energy is conserved, Total energy of the isolated system is conserved. Conserved means unchanged. Conserved means unchanged, right? Then from that law, from the law of conservation of energy, we can get, right? The idea we can have is this, right? From above. Therefore, from above, right? Total energy is conserved means that is unchanged, no? Right? Idea is this: total initial energy equals total final energy, right? So we will be using this idea when we move ahead with questions. We will be using this idea, and this is valid for any number of points. That doesn't matter, because if there is unchanged, it should be unchanged at each and every point, no? So therefore, for any point also, this idea is valid. Valid for any point. For any point also, it is valid. Okay, take it down. Right? Total initial energy equals total final energy. So if needed, you can highlight. If needed, you can highlight. This is the idea of conservation of energy, right? So if you don't know, conserve means, right? If needed, conserved means constant, constant or unchanged. Conserved conserved means constant or unchanged, right? Now we are going to apply this here for this question. Close the note. Now the note is done. Close the note. Close the note. Close the note. And let's go to method 2. See? And let's go to method 2. Method 2. Method 2. Using, right? This will be using law of conservation of energy. Using law of conservation of energy, right? Okay, look at here. Now, if we are to use law of conservation of energy, right? All the types of energy forms, right? All the types of energies, all the forms of energies should be considered. It should be considered. And minimum, we have to have 2 points, right? So without having 2 points, you can't equate them, no, make it equal, no. So therefore, minimum you have to have 2 points, right? And when you are writing potential energies, gravitational potential, when you are writing gravitational potential energies, you have to introduce an earth zero level. We have to introduce an earth zero level, right? Okay. Then for the earth zero level here, for this question, I will introduce this level, right? I will introduce this level as earth zero level for this particular question, right? Earth zero level, right? Now, using law of conservation of energy, total initial energy equals total final energy, no? State the same argument. Total initial energy equals total final energy, right? Initially, this is at A, which means total energy at A equals finally it is at B, total energy at B. Total energy at A equals total energy at B, right? So when you write total energies, you have to write all the forms of energies. Now in this particular question, right, in this particular question, only gravitational potential and kinetic energies are involved now. So if there are sound energies, if there are heat energies, strain energies, or anything else, you have to write everything here when you are writing energies. But here there are only two energies, right? So therefore we'll be focusing on these two energy types. So one is gravitational potential. When the object is here, look at the board. When the object is here, so we know gravitational potential energy is written as mgh, and h is the most important term there in mgh, right? H is the vertical height from earth zero level to center of gravity of object, right? Now here we are considering a particle. Since we consider a particle, center of gravity and the particle will be same. But if a non-particle object is given, they will be different. If a non-particle object is given, they will be different. That's the idea. That's the idea, right? Okay. Then in mgh, h is the vertical height from earth zero level to center of gravity. Now earth zero level is here. Object is here, so the center of gravity of the object is here. Right? When you measure distances above the earth zero level, they are considered as plus. When you measure distances below the earth zero level, they are considered as minus. Then here there is a non-zero gravitational potential energy, right? It can be written as mgh, above no plus h, plus h. But initially this is at rest. At rest, if there is at rest, no kinetic energy. If that is at rest, no kinetic energy, right? And at B, the particle is at the earth zero level. At the earth zero level, we know h is measured from earth zero level now. Now, when h is measured from earth zero level, the particle is at earth zero level, which means h is zero. H is zero. Since h is zero, mgh is zero now. Plus, there's a velocity. Since there's a velocity, a non-zero kinetic energy is there, half mv squared, right? So if you need more clarity, I have written the potential energy here, right? I have written the potential energy here and kinetic energy here, and this side also potential energy first and kinetic energy here, like this. Right, now simplify this. Mgh equals half mv squared, m to m cancels, right? V squared equals 2gh, v equals root 2gh. See, same answer comes either way. So since it was a linear motion, we were able to use linear motion equations as well. And now today we are learning about energy, applications of energy, right? So using energy also, we can do the same like this, right? Raise your hand if it's clear. Raise your hand if it's clear. Right? Okay, take it down. And about selecting the earth zero level, right? We will come to the discussion again after this one. First, take this down. right? Okay, write down below. Write down below. Any arbitrary level, any arbitrary, any arbitrary level, any arbitrary level can be considered. Any arbitrary level can be considered as Earth zero level. Any arbitrary level can be considered as Earth zero level. Any arbitrary level can be considered as Earth zero level. Just now only I noticed that I haven't turned on the recording on Zoom, right? So if you notice that the recording on Zoom is not on, please remind me, right? Because when you are sitting in front of your device, you will clearly see it, no? Right? So just now only I noticed it. The recording is not on, right? So again, if you notice such a thing, please remind me, right? For today, it will be fine because it's already streamed to YouTube. So therefore, it will be stored on YouTube. But if it was another day, I mean a different day that I was not streaming to YouTube, right? You won't get any recording after the class. So keep that in mind. So if I forget to turn on it, please remind me. Right? Okay. Any arbitrary level can be considered as Earth zero level. Any arbitrary level can be considered as Earth zero level. Any arbitrary level can be considered as Earth zero level. Based on the requirement. Based on the requirement. Based on the requirement. See, now this is what happens if we consider Earth zero level here, right? At this level, we can do the same considering a different Earth zero level as well. See, so this is the idea you should know. This is the idea you should know. The Earth zero level you are selecting, the Earth zero level you are selecting is irrespective of the answer. It is independent of the answer. Now let's say I need to select this level as Earth zero level. See what happens. Object is here at A and comes down to B, right? And this total is H. And I'm going to assume this as located X distance above. If it is located X distance above, right? X distance above or below, this part will be H minus X, no? Because total is H. Total is H. Then if this is X, this is H minus X. See, now in this case also, you can apply energy the same way that we applied before. And accordingly, you have to write all other terms. According to your zero level, you have considered, you have to write all other terms like this. See, total energy at A equals total energy at B, no? Then gravitational potential energy plus kinetic energy, right? And here also gravitational potential energy plus kinetic energy. At A, look at the board. At A, particle is not at the earth zero level. Then there's a non-zero value. Distance is measured upwards. If the distance is measured upwards, there is a positive value, right? Positive h, positive value means positive h. Then mg into positive h minus x, gravitational potential energy up to this point. Plus, since there is no velocity, there is no kinetic energy. Then here at B, gravitational potential energy. If there is not at the earth zero level, there is a non-zero gravitational potential energy. It is non-zero now. There is a non-zero gravitational potential energy. If there is not at the earth zero level, then earth zero right? That is above earth zero level now. Sorry, that is below earth zero level now. Right? So therefore, if there is below earth zero level, when you measure the distance below earth zero level, h is minus, h becomes minus, then it should be mg times v not x minus x, mg times minus x, right? Plus there's a velocity there, half mv square, simplify this and see mgh minus mgx equals, here also this is minus mgx plus half mv squared, minus mgx to minus mgx cancels. Now again, see, the same answer comes. M to M cancels, V equals root 2 GH. Same answer comes. So therefore, the idea is, listen, the idea is your final answer will not be affected. Your final answer will not be affected by the earth zero level you are selecting. But number of lines, number of steps, number of lines actually in your simplification can differ, and it will differ. Number of steps in the simplification will differ, right? But the same answer comes. Now from these two applications we did, right? As an idea we can say, right? I mean, as a rough idea we can say, right? As a rough idea we can say, considering the lowest possible level of the system is easier. Considering the lowest possible level of the system is easier when you select zero levels, but not bounded to that, not framed to that, right? There are places, there are contexts where considering some other points, some other levels would make it easier. So therefore, you have to know this. That's why I discuss both of them. You have to know this, right? And contextually, based on the context, you should be able to select a proper zero level, right? That is the idea we have to take from here. Take this down. Take this down. Take it down. Okay, write down below. Write down below. Choosing lowest possible level. Choosing lowest possible level. Choosing lowest possible level of the system. Choosing lowest possible level of the system. Choosing lowest possible level of the system choosing lowest possible level of the system as Earth zero level, as Earth zero level is easier, is easier in most of the cases, is easier in most of the cases, is easier in most of the cases. Is easier in most of the cases. Right? Is easier in most of the cases. Okay, right. So that's the idea. That's the idea. Otherwise, there are no any rules behind selecting Earth zero level. There are no rules, right? Usually, selecting the lowest level is easier, right? So otherwise, even if you didn't select the lowest level, likewise, if your application is correct, if your application is proper, if your application is correct, you will get the unknown terms and they will be cancelled off from the calculation, and again you are going to get the same answer, right? Raise your hand if there is all clear up to this point about this now, right? About the application. Raise your hand if it is clear. Okay. Others? Okay. Afil, what about you? Right. Okay then. So there are a few more examples to be discussed, examples and a few more question types to be discussed, right? So before moving on to the other types of questions, first we'll be taking a break. We'll be taking a break and we'll be meeting back after the break. We'll be meeting back after the break, right? So we'll take the break from this the break. And listen, we'll be spending the entire day with, we'll be spending the entire day with energy, right? So everything regarding energies will be needed, right? So therefore, again, go through the note if you are not going anywhere during the break, right? So if not, you can just go out and make yourself refreshed, have something. And if you are feeling sleepy, you can wash your face, right? And if you need anything with you around you, right? If needed, you can have something and come back, right? Now it's 7:40. So we will take a break of 20 minutes. Let's regroup again at 12, right? So go and come back by 12, right? Okay. Okay, we'll start. I'm audible again, right? Okay, right. Example 2. Example 2. Write down. Write down. A sphere of a metal sphere. A metal sphere of a metal sphere of a metal sphere of radius symbol r. A metal sphere of radius symbol r is released from rest. A metal sphere of radius symbol r is released from rest. Is released from rest at a point located at a point located at a point located simple h distance above ground. At a point located simple h distance above ground. At a point located simple h distance above ground. At a point located simple h distance above ground. Right? Simple h distance above ground. Determine its velocity when it reaches 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 ground. Okay, take down the diagram and try it quickly. Try it and send me your answers. Okay, anyone? Any answers for this one? Only given data H and R, only given data H and R, and other than that, G can be there anyway, right? Nothing else. Nothing else. Anyone? See, now in this kind of a case, if you need to apply energy, right? Now I'll consider this as a zero level, right? I'll consider this level as a zero level, right? And for the ease of writing, ease of considering, we'll consider this as point A and this as point B. So we know this undergoes a linear motion like this, and it will reach ground. It will reach ground like this. It will reach ground like this, right? Like this. Okay, and we need velocity of this ball when it is reaching ground. Let's say V, right? Then apply energy using law of conservation of energy. Using law of conservation of energy, we can say total energy at A equals total energy at B. Total energy at A equals total energy at B, right? Total energy at A, there's a potential energy, right? From Earth zero level to center of gravity, height is h, then that is mgh, released from rest. No kinetic energy, no kinetic energy. At B, object is here, Earth zero level is here, so there's a distance between Earth zero level and center of gravity of the object, then that is mgr, right? Up to center of gravity, no, mgr plus there's a kinetic energy with this velocity v, half mv square. Divide the entire equation by m cancels, right? Then gh equals gr plus v squared over 2, right? Take it to the other side and take g out, h minus r, cross multiply by 2 equals v squared. So v is root 2g h minus r. V equals root 2g h minus r, right? So if a non-particle object is given, that is the idea. If a non-particle object is given, this is not a particle, radius is given, right? So in the description, usually it won't give whether it's particle or non-particle, right? So if a radius is given, that is a hint to you to consider it as a non-particle object. If there is a particle, no radius will be given, right? So radius if the radius is given, that is non-particle. So when it reaching ground, center of gravity is here. So likewise, it should be factored. Take it down. Right? Write down below with the red pen. Mention this below with a red pen. Mention this below with a red pen. H in MgH, simple H in MgH, simple H in MgH, simple H in MgH is simple H in MgH is the vertical height from is the vertical height from Earth 0 level to vertical height from Earth 0 level to vertical height from Earth 0 level to center of gravity, Earth 0 level to center of gravity of object, Earth 0 level to center of gravity of object. Right. Example 3. Example 3. Okay, write down. Write down. A particle is a particle is a particle is given a velocity, sorry, speed. A particle is given a speed. A particle is given a speed of 2 ms minus 1 is given a speed of 2 ms minus 1 at A and let it travel along the path AB and let it travel along the path AB along the path AB. If all surfaces are smooth, right? If all surfaces are smooth, if all surfaces are smooth, if all surfaces are smooth, determine velocity of object, sorry, velocity of particle, determine velocity of particle at B. 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 Right. Take this down. Take this down, and I will give you 2 minutes. Right. I will give you 2 minutes. Right. And send me your answers. I need velocity of the particle at B. Need velocity of the particle at B. Quickly. 2 minutes. Send me your answers. Any answers? Anyone? Quickly. Now it's your turn. Yeah, it's your turn now. Anyone before I start? Anyone before I start? No? Are you still trying or shall I start? Quickly. Are you still trying or shall I start? Right. See, if you are using energy, listen, if you are using energy, it doesn't matter whether it's a linear motion or a circular motion or kind of a curved motion, a projectile, doesn't matter. Doesn't matter because for the conservation of energy, only thing what we need is 2 points, right? Only thing what you need is 2 points, right? If you have 2 points, you can apply energy. You can apply conservation of energy, right? The only requirement is you have to have 2 points. That's it. You have to have 2 points. Now, in this case also, that's same, right? Then we can say, so let's say when the object is here, when the particle is here, let's say the velocity is v, say velocity is v, right? We just need 2 points now. Then using, right? Same thing, law of conservation of energy. Law of conservation of energy, right? Total energy at A equals total energy at B. Total energy at A equals total energy at B. Since heights from this level is known, right? I will consider this as at zero level. I will consider this as at zero level, right? Total energy at A, potential energy. There's a potential energy M, G is 10, H is also 10, plus there's a kinetic energy at A. There's a non-zero kinetic energy at A, half mv squared, half m v squared, then 2 squared equals at B. There's a potential energy as well, m g h plus there's a kinetic energy half m v squared, right? So if this substitution is done, right, which means like 75% of the question is done here, right? Hereafter, that is just a simplification. Divide the entire equation by m to m cancels, right? Then nothing else cancel now. Let's simplify this way. 10 times 10, 100 plus 2 squared is 4, 4 over 2 is 2, right? Equals 10 times 6, 60 plus here v squared over 2. Simplify. V squared over 2 equals, this is 42. Then v squared equals 84. V equals root 84. Root 84. Root 84 can be written using 4, no? Right? Root 84 can be written using 4 as how? 21. 21 times 4. So this is 2 root 21, right? 2 root 21 ms minus 1. 2 root 21 ms minus 1, right? So the idea I wanted to give you from this question is, from this example is, for energy, if you have to apply energy, it doesn't matter which type of a motion that is, right? The only thing matters is whether there is an energy loss or not. If there is an energy loss, you can't use energy. If there is no energy loss, you can use energy. Take it down. right? Okay, understood? Understood? Is it clear? Raise your hand if it's clear. Okay, write down below with a red pen. Write down below with a red pen. The nature of motion, the nature of motion, the nature of motion, the nature of motion, the nature of motion doesn't matter when applying the nature of motion doesn't matter when applying conservation of energy, when applying conservation of energy, as long as as long as as long as there's no energy loss, as long as there's no energy loss, as long as there's no energy loss, as long as there's no energy loss. Within brackets, having minimum two different points within brackets, having minimum two different points, having minimum two different points, having minimum two different points is enough. Having minimum two different points is enough. Having minimum two different points is enough. Right. Okay. Let's start few questions. Right. Examples are done. Now let's start few questions and see. Right. Question 1, write down. So in the tute also I have put more questions. Right. Tutes are posted. You will receive the tute before the next class. Right. So usually within 3 days you will get it. Right. So you will get the tute before the next class, and next day only we will be needing the tute, right, to do the questions in the tute. Yeah, we should get two tutes this time, one for linear momentum and energy this lesson, and the other one for equilibrium of forces. That is coming up. That is a coming up lesson, right? So you should get two tutes for the month. Okay, question 1, write down. Question 1. Question 1. Okay, write down, write down, write down. A particle is released from rest. A particle is released from rest. A particle is released from rest. A particle is released from rest at point A. At point A. At point A. If all surfaces are smooth, 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 determine, determine, determine velocity at object, determine velocity at object at B and C, determine velocity at object at B and C, determine velocity at object at B and C. Right? Take down the diagram and start the question. Right? I'll start the discussion in 3 minutes. So I need all of you to send the answers. Right? Send me the answers because then only I can see whether you have understood this or not. That's the thing. Right? So in the revision, we know lessons are going usually as daily lessons, right? Unless there is a kind of a large lesson. So daily in the daily basis during these like 6 hours of time, around 6 hours of time, right? We'll be covering that particular part. So therefore, by the time you are leaving the class, at the end of the class, by the time you are leaving the class, right? You should be comfortable with what we discussed today, right? So that is how you progress now. That is how you improve, right? So therefore, send me your answers before I start. Start now. Need all of you to get the answers and send the answers. Send your answers. Right, anyone? Okay, good. Let's see. Good. Since labels are given, no need to convert G. Since labels are given, no need to convert G. Right? Labels are given. No? So if labels are given, we can keep labels. We can keep labels throughout. Capital H and simple H. Labels are given. Right? Velocity at B. If you need velocity at B, use energy for points A and B. Right? Using law of conservation of energy. Right? For A and B. Total energy at A equals total energy at B. Right? I will consider this level as Earth zero level. This level as Earth zero level. Right? Horizontal level. Then mgh at A is mg capital H plus there's no kinetic energy because it is released from rest, it says. And at B there's a velocity. I will label it as VB for my is right VB. Then there's a potential energy as well above the Earth zero level, mg simple H, right? Mg simple H and plus half mv squared. We can say divide the whole equation by m, it cancels. Then take G out while taking this to the other side, G is plus V squared over 2. G is common. Then H minus H equals V squared over 2. Right? So this is actually VB squared, VB squared. So VB equals root 2G capital H minus simple H. 2G capital H minus simple H. Right? Root 2G capital H minus simple H. Right. And then we need velocity at C. Right? So let's say velocity at C is Vc. Right? So when you are using, you can use either B and C or A and C, that doesn't matter. Right? So either way it will be same. Either way, it will be the same impact, same thing. Because conservation of energy is valid for any 2 points, no? Conservation of energy is valid for any 2 points. So if you need to use for A and Z, use for A and Z. If you need to use for B and Z, use for B and Z. Right? If you apply it accordingly, when you apply it accordingly, right? At the end of the day, you are going to get the same answer. All of you are going to get the same answer at the end of the day. Right? See? Then I will be using A and Z. Doesn't matter. You can use any 2 points. Total energy at A equals total energy at C. Total energy at A, potential energy, mgh plus no kinetic energy. At C, there's no potential energy, but there's a kinetic energy. Half m Vc squared m2, m cancels. Vc squared equals 2gh. So Vc equals root 2gh. Right? A simple application, right? Conservation of energy is a simple application. So once you understood the basic concepts behind this, give me 1 minute. Once you understood the basic concepts behind this, the application is easier. As an application, the approach is easier. Take it down. Right. Now, from the example one, right? From the example one we did, and using this one, right? We can see a pattern here. When we find these velocities, right? The pattern is this. When we consider motion under gravity, in example 1, you got root 2gh now. When you consider the motion under gravity. Now, this is a motion along a smooth path. When I consider the motion along a smooth path, at B, we have got root 2gh minus h. Right? So, where capital H minus simple h is the vertical fallen height. And when we need the velocity at C, you have got capital H. Right? So, fallen vertical height is capital H. So, likewise, this is valid for any motion under gravity or motion travels along a smooth path. This is valid. Always you can write the final velocity as, right? If it is starting at rest, always you can write the final velocity as root 2g into the fallen vertical height. That's a pattern we can see. Right? So, write down below with the red pen. If an object travels, under gravity, or along a smooth path, under gravity or along a smooth path. under gravity or along a smooth path. Under gravity or along a smooth path. Starting from rest. Along a smooth path, starting from rest. Starting from rest. Along a smooth path, starting from rest. Its velocity at any point can be written as its velocity at any point. Its velocity at any point can be written as its velocity at any point can be written as its velocity at any point can be written as v equals root 2gh. V equals root 2gh. Where v equals root 2gh. Where h. Where h. Define h. Introduce h. Write down. Where h. Fallen vertical height. Fallen vertical height. Fallen vertical height. Fallen vertical height. Right, fallen vertical height. It's clear enough, right? Keep this in mind. Keep this in mind. At times you can use it for MCQs, right? Because like popularly, more frequently, these MCQs are coming, right? From maybe linear motion, from energy or wherever, right? If you need it, you can use this at once, right? You can use this at once. Let's move on. Let's move on. Right, question 2. Question 2. Write down. Write down. An electric motor. Write down. An electric motor. An electric motor. An electric motor pulls. An electric motor pulls 100 kilogram mass. 100 kilogram mass. 100 kilogram mass to a height of to a height of to a height of 20 meters. To a height of 20 meters. To a height of 20 meters. In, right, in, to a height of 20 meters in 4 seconds. To a height of 20 meters in 4 seconds. What is the minimum power? What is the minimum power? What is the minimum power required? What is the minimum power required? What is the minimum power required for this motor? What is the minimum power required for this motor? What is the minimum power required for this motor? What is the minimum power required for this motor? Right. Right. 2 minutes again. Right. 2 minutes. Two minutes again. Right. Anyone before start? Anyone before I start? Okay. Anyone before I start? Any answers? Any answers before I start? I asked about the minimum power. Minimum power. I asked about the minimum power. No? Are you still trying or shall I start quickly? Tasmida, any answers? Afil, any answers? Hamza, any answers? On. All right. See, that is about power. No, this is how you should think. So we know general equation of power is, that is about power. General equation of power is either work over time or energy over time. No, right? So I will approach using work over time. Now, to get an idea, this is what is done by the electric motor now. We have a weight of a mass of 100 kg, right? We have a mass of 100 kg. 100 kg, no? Then its weight is 1000 newtons. And if the motor applies a force to take it up, right? Take it up, minimum value of this force should also be 1000, no? We got that idea before. And this is going to lift up by 20 meters, something like this, 20 meters. Fine. Now, we know minimum force to say lift this, minimum force to lift is when F equals 1000 newtons, no? The minimum force, right? So knowing that, listen, knowing that, you can apply the equation of power, right? We have two equations for power. One is work over time, or other one is P equals Fv, right? Force into velocity. Now, since a velocity is not given, my approach is to use W over T, right? Work over time. Then we know power equals work over time. But we know work can be written as force into displacement over time. See how easy the question is if you understood these things, if you can understand these things. Very easy, right? Then this is force into displacement over time. Now force is known. Minimum force required is the adequate force for the minimum power, no? So that is 1000. Displacement is 20 meters, right? And time it takes is 4 seconds. See how easy? Then 4 times 5 is 20. Then there is 5000 watts. This means we can say that is 5 kilowatts. Minimum power required for that motor is 5 kilowatts. Something like that. 5 kilowatts. Right? Very easy. Just a plug and play. If you understand this scenario, what is given properly. Right? Such cases are there. Okay, is it clear now? Raise your hand if it's clear. Raise your hand if it's clear. Okay, good. Write down. right? So as I told you, we are starting the reverse class this Saturday, right? So it will be happening on this Saturday, 10th of January, from 7 p.m. to 10 p.m. right? 7 to 10. And we are starting the reverse class with what's the lesson? With properties of matter, unit 10, right? Unit 10, properties of matter. And we'll be starting surface tension there. We'll be starting surface tension there in properties of matter, right? You can share the message, pass the message with your friends. And 1 second. Okay. So you can pass the message, share the message with your friends. And for all of you, you have registered for the revision class. You can join the reverse class free, right? Okay, to do this, another possible way is, forget the board, another possible method is, right? As an alternative method, another possible method is, we know, listen, we know transfer of energy equals work done, no? Transfer of energy. Now, when it is here, there was no energy stored there, but when it is here, when it is taken to here, the potential energy is stored. Then power can be written as transfer of energy over time. Stored potential energy at here is mgh. No kinetic energy, mgh over t. Right? This is also fine. Right? M 100 g h over time. Same thing. Same thing. 4 times fire. See? Right? So that is also fine. Because that's why we proved that transfer of energy equals amount of work done. So either way it's correct. Either way it's correct. Take it down to. Okay, that's a simple question. I don't think you need any explanations about this question further, right? A simple question. Let's move on. Question 3. Question 3, write down. Question 3, write down. Two particles A and B. Two particles A and B. Two particles A and B have equal kinetic energies. Two particles A and B have equal kinetic energies. Two particles A and B have equal kinetic energies. Two particles A and B have equal kinetic energies. Two particles A and B have equal kinetic energies. But the velocity of particle B is, but the velocity of particle B, but the velocity of particle B, but the velocity of particle B is 4 times. Velocity of particle B is 4 times that of A. Right? Velocity of particle B is 4 times that of A. Velocity of particle B is 4 times that of A. Velocity of particle B is 4 times that of A. What is the ratio between? What is the ratio between? What is the ratio between linear momentums? What is the ratio between linear momentums? What is the ratio between linear momentums? What is the ratio between linear momentums of these two particles? What is the ratio between linear momentums of these two particles? Right? Ratio between linear momentums. Okay, again, 3 minutes, right? 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 One to 16, a possible value, a possible value. Any different answers? Okay, shall we see? Right. So it says they have equal kinetic energies. Okay. Now at that point itself, I'm going to start the question. See, so at the same point, we can start. Kinetic energies are same. Then kinetic energy of A equals kinetic energy of B. No, kinetic energy of A equals kinetic energy of B. And here there was another data given for velocity of B is 4 times that of A, right? Which means this is also given. Velocity of B is 4 times that of A. Velocity of B is 4 times that of A, 4VA. Right? That's a given data. Right. Then you can expand kinetic energies. And what about their masses? Are they equal or different? What about their masses? Equal or different? What about their masses? Masses are definitely different. Right? Definitely different. Velocities are different, no? So otherwise, how come kinetic energies are going to equal? Right? Masses are different. Right? And unless it is given as identical law, equal masses or something like that, always we have to consider it as different as well. Right? Okay, then kinetic energy of A, half, say mass of A is MA, VA squared equals, we can write this as half MB VB squared. Right? Half to half cancels. Half to half cancels. Right. Now, what we need is this, no? Say, this is my final target. Linear momentum of A, MAVA. Linear momentum of B, MBVB. This ratio is our final target. This ratio is our final target. Now, VA to VB is already known. Then if I can find out something for MA to MB ratio, for the ratio MA to MB, by combining those two, we can arrive at the final answer. No? So that is how I think. That is the way I think. Right? Then my target is getting something for masses, ratio between masses using this. Right? Getting something for ratio between masses using this. See? Let's do this way. Substitution lazy. MA, fine, times VA squared equals MB times VB squared, but we know VB is 4VA, no? Then this is 4VA whole thing squared. Right? Simplify. MA VA squared equals MB 4 squared is 16 VA squared. Right? VA squared to VA squared cancels. Right. I'm interested about MA over MB. Then from here, MA over MB equals 16. No? MA over MB equals 16. Right. So I will keep this as 1. I will keep this as 1. And from this ratio, I know, see, from this ratio, I know VA over VB. From this, VA over VB equals 1 over 4. We'll give it as 2. See, now we can easily arrive at the final answer. This is MA over MB times VA over VB, no? Right? So MA over MB is 16. VA over VB is here 1 over 4. Then there is 16 over 4. So the ratio between these two is 4. Ratio between these two is 4. Got it? Got it? Another kind of a simple but regular, frequent type of questions you are getting from these areas. Write down. Okay, finish. This is not the only way of doing this question, right? You might have your own methods, right? That is totally fine. That is totally fine, right? So this is what I saw. This is what I saw. Right? Okay, listen. So we can come up with this kind of a relationship as well. Okay? We know kinetic energy is, let's say K. Kinetic energy is K. K is half mv squared, no? K is half mv squared. Now, if we need to create linear momentum in kinetic energy, because this is a popular question type, since this is a popular question type, right? You can keep this in mind. If you need to create linear momentum, right? This is also a possible approach. What you can do is K equals half, right? If I write this as m squared v squared over m, no change, no? No change. Right. Now, my requirement is satisfied. We know linear momentum is mv. Linear momentum is mv. Then K equals, kinetic energy equals, this is 1 over 2m. And this is mv whole thing squared. But mv is p. Then kinetic energy equals 1 over 2m p squared. right? So kinetic energy can be written as P squared over 2m if needed. Kinetic energy can be written as P squared over 2m if needed, right? So that is also a possible equation you can use when solving such type of questions, right? Make solve කරන්න පුළුවන් easily. But easily you can solve this using this as well. But easily making solve කරන්නත් පුළුවන්. So take it down as well as a note. Let's move on. Okay. What's the question? Number 4, eh? 4. Write down a cricket ball. A cricket ball. A cricket ball is hit for a 6. A cricket ball is hit for a 6. A cricket ball is hit for a 6. It leaves the bat. It leaves the bat. It leaves the bat at an upward angle. At an upward angle. It leaves the bat at an upward angle. It leaves the bat at an upward angle. It leaves the bat at an upward angle of 45 degrees. At an upward angle of 45 degrees to the horizontal, 45 degrees to the horizontal with kinetic energy K. To the horizontal with kinetic energy K. With kinetic energy K. With kinetic energy K. With kinetic energy K. What is the kinetic energy of ball? What is the kinetic energy of ball? What is the kinetic energy of ball at the maximum point of its flight? What is the kinetic energy of ball? What is the kinetic energy of ball at the maximum point of its flight? What is the kinetic energy of ball at the maximum point of its flight? At the maximum point of its flight. Okay. Right. Start it. These are combination of projectile motion with energy. Projectile with energy. 3 minutes. Right. 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 Any answers? So we will spend like the first hour of next day with the questions of energy, right? Right. We will spend the first hour uh, of next day with the questions of energy, and next day we are going to start linear momentum, the next main part we have, right? So now you should also get two answers. Any answers? Okay. Anyone before I start? Anyone before I start? Anyone before I start? No? Okay. See, time is enough. Time is enough. Okay. This is about a cricket ball, right? So it says it leaves the bat. It leaves the bat. We don't know what the velocity is. Let's say u with an upward angle 45, right? And you asked about the kinetic energy at the topmost point, highest point here, right? Kinetic energy here, right? So what we know from projectiles is, right? One very important thing about a projectile is, so we discussed projectile motion on the second day of this revision class, right? Second day of the revision class, projectile motion. One very important thing is horizontal velocity component of a projectile is always unchanged, right? Now, here, if you dissolve this, right? If you dissolve this, we know we have u sine 45 and u cos 45. Then the horizontal component becomes u cos 45. That remains unchanged. That remains unchanged. And since this is the maximum point, vertical velocity component becomes 0. Vertical velocity component becomes 0, right? And another data was given as kinetic energy at the initial point is given as k, no? Kinetic energy at the initial point is given as k. Energy is a scalar, right? No in direction. Then velocity at the initial point is u, which means this is what is given. K equals half m u squared. This is given. K equals half mu squared. This is a given data. K equals half mu squared, right? This is a given data. So I will label this as 1 given and then check the kinetic energy at this point. Let me label this point as point A. Then we need kinetic energy at A. Let's say kinetic energy at K is K dash. Initially it was K, no? Kinetic energy at A is K dash. Then K dash should be half same mass because same object. Velocity at that point, vertical one is 0, then only horizontal component remains u cos 45. Then u cos 45 squared. U cos 45 squared. Right? Then k dash equals half m. This is u squared. And cos 45 is 1 over root 2. 1 over root 2 squared. Right? Cos 45 is 1 over root 2. 1 over root 2 squared. Simplify this. Then k dash equals half m u squared into square of 1 is 1. Square of root 2 is 2. See, now what has happened? Half mu squared is created here. Half mu squared is created. We know half mu squared is k according to given data. Right? Half mu squared is k according to given data. Then subject this from this, which means k dash equals, this part is k, no? K over 2. K dash equals k over 2. K dash equals k over 2. Right? Again, a simple approach. Take it down. Okay, write down below with a red pen. Write down below with a red pen. Horizontal velocity component of a projectile. Horizontal velocity component of a projectile. Horizontal velocity component of a projectile remains unchanged. Horizontal velocity component of a projectile remains unchanged. Horizontal velocity component of a projectile remains unchanged. Right? Horizontal velocity component of a projectile remains unchanged. Second point, keep using red. Second point, vertical velocity component becomes 0. Vertical velocity component becomes 0 vertical velocity component becomes 0 at the maximum point. Vertical velocity component becomes 0 at the maximum point. vertical velocity component becomes 0 at the maximum point. Vertical velocity component becomes 0 at the maximum point. Okay, those two are the two logics I use from projectiles, right? And this is a simple application of energy again, a kinetic energy, a very simple application of kinetic energy. Okay, question 5. Question 5. Write down. A car travels. A car travels. A car travels. A car travels with a speed of 10 ms minus 1. A car travels with a speed of 10 ms minus 1. A car travels with a speed of 10 ms minus 1 on a rough horizontal road. On a rough horizontal road. On a rough horizontal road. Rough horizontal road. With power output of engine. With power output of engine. With power output of engine 1 kilowatt. 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 Right? Power output of engine 1 kilowatt. Now it enters. Now it enters. Now it enters a hill area. Now it enters a hill area. Now it enters a hill area. Hill area with angle of inclination. With angle of inclination. With angle of inclination 30 degrees. With angle of inclination 30 degrees. Enters a hill area with angle of inclination 30 degrees. Right? Enters a hill area with angle of inclination 30 degrees. Hill area with angle of inclination 30 degrees. If mass of car is 1000 kilograms. If mass of car is 1000 kilograms and if mass of car is 1000 kilograms and if mass of car is 1000 kilograms and frictional force remains unchanged throughout the motion, and if frictional force remains unchanged and frictional force remains unchanged throughout the motion, frictional force remains unchanged throughout the motion, frictional force remains unchanged throughout the motion, determine required power output by engine. Determine required power output by engine. Determine the required power output by engine to climb up the hill. To climb up the hill. To climb up the hill with the same speed. to climb up the hill with the same speed. To climb up the hill with the same speed. To climb up the hill with the same speed. Okay, give it a try. So in the first part, it travels in a horizontal road, right? Horizontal road with 10 ms minus 1 and say friction is simple F, right? If the friction is simple F, the traction force by the engine is capital F, right? Fractional force by the engine is capital F. And in the second scenario, it climbs up a hill of 30, right? So mg acts, and here one component of mg acts downwards the plane, mg sine 30. Other than that, friction acts, that is same as before, it is given, and say new fractional force is F dash, and this needs to go up, climb up with 10 ms minus 1, same, with the same 10. Needs to climb up with the same 10. So let's assume this new fractional force as F dash, right? So I'll give you a hint. Try to use the equation P equals Fv. Try to use the equation P equals Fv. That is a hint. Try now. Try to use P equals Fv. Right? Now, if you use the equation for the first scenario, see what's happening? For the first scenario, P equals Fv for the first scenario, right? I gave you power as 1 kilowatt. 1 kilowatt is 1000 watts, right? And we know in this scenario, if it is moving with 10 ms minus 1 uniform velocity, capital F equals simple F, no? Capital F equals simple F, right? Capital F equals simple F. Then simple F times V is 10. So the value of friction can be determined. 10 to this cancels. So friction has been 100 newtons. Friction has been 100 newtons. Now you can apply the same considering the second scenario. P equals Fe again now. This was applied for the horizontal motion. This is for the upward motion, right? Upward motion. Upward motion. Now we need required P, let's say P dash in new scenario, second scenario, right? And now in this scenario, if it travels with 10 ms minus 1 upwards, uniform velocity, F dash equals F plus mg sin theta, no? Right? Then say F dash V, but we know F dash equals mg sin 30 plus F, right? Travels with uniform velocity. There shouldn't be any unbalanced force. Simplify. That's it. P dash equals F dash is mg sin 30 plus F. Then plug those values. Mg. Mg was mass is 1000. So mg is 10,000. 10,000 sin 30 half plus friction 100 V 10. So P dash equals, this is 5,000 plus 100 is 5,100. 5,100 into 10. So P dash equals this much. P dash equals 51,000 watts. So that is 51 kilowatts. 51 kilowatts. So if this car needs to climb up with the same speed, this engine must be able to give a power of 51 kilowatts. It must be able to give a power of 51 kilowatts. Right? It must be able to give a power of 51 kilowatts. That's the idea. That's the whole idea. It should be able to give power of 51 kilowatts. Okay, raise your hand if it's clear. Right? This is a use of P equals Fv. So likewise, if velocities are given directly, you can go with Fv. Mention below in red. Mention below in red. Use P equals Fv. 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 If power and velocities are given. 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 Okay, listen. Right. So after covering the theory parts in energy, right? Now these questions we discussed today are the not the average but the simple questions, right? Not the average, the simple questions in energy, work, power, and energy, right? And the other questions starting from average to advanced, right? All of them are there in the tube, right? And next day, first plan is we'll be first finishing off all questions of energy, right? First plan is we'll be finishing work power energy questions, work power energy, and then we'll be starting linear momentum. We'll be starting linear momentum, and then applications of linear momentum, and then applications of combinations of linear momentum and energy, right? Applications of combinations of linear momentum and energy, right? So that's a plan for next day, right? That's a plan for next day. The main part we are going to start is linear momentum, right? And reminding again, we are starting the reverse class on Saturday, right? So make sure you are joining the class on time, right? It will be from 7 to 10. That's a reverse theory class, right? So if anyone you can share the message, you can take my flyers from the channels. All right. Any questions before winding up? Any questions before winding up? Right. So if there's no any questions, we'll wind up the class here, right? So study hard, be safe, study hard, work hard. We are 30 weeks ahead of the exam now, right? Utilize these 30 weeks to the fullest, right? So always your final result will be the reflection of the amount of effort, amount of work you did during this period, right? So don't even waste a second or a minute of time you have, right? Utilize everything for your studies. And this is a good point to restart yourself, because now this is a new year, no? So we are starting a new year with new hopes usually. We are starting a new year with new hopes, new blessings, new targets, new goals, right? So at the beginning also I explained this a bit. So therefore, turn this around, turn your results around, turn yourself around, and make a new version of yourself, right? Make a new version of yourself starting from today. Starting from today, if you haven't done the things yet, right? Which means if you are already on the track, you can ignore this, right? If you are already on the track. But what I'm saying is, if you are not on the track, if you feel like you don't get the required marks for the papers, right? Sometimes you are getting stuck when you are writing questions. Sometimes you don't get questions, right? So even if you know the theory, you don't get the question how to approach, right? So those are the things that you can notice whether you are on the track or not, right? So if not, don't wait further, just start today itself and continue this momentum, continue the rhythm until your exam, right? All right then. Then if no any questions, we'll wind up. Okay then, good afternoon and see you in the next class, right? Goodbye.